Okay, we've been talking about hypothesis testing now for several meetings, talking about hypothesis testing using z-tests or using a z-test as our departure point, and we've now moved to the use of t-testing that is appropriate when sample size is small. And what I want to do this morning is go over another couple of examples of t-testing. I'm concerned, I'm interested that you understand the process of hypothesis testing, and then obviously at some lower level the mechanics of, in this instance, t-testing. As I've indicated, I think several times, hypothesis testing is a three-step process. The first step involves deriving the critical value of the test statistic, whether that test statistic is z or t, or as we will come to see in analysis of variance, an F statistic. The second step in the process is to compute some critical value, or some observed or attained value rather, of that test statistic. And the third step is then to use those two scores to evaluate the null hypothesis. And while I'm confident that you can, if you memorize the formula, compute an obtained value of the test statistic, whether it be z or t, I'm not altogether convinced that all of you can proceed effectively through the other two steps. And having said that, I would encourage you, if you have questions, if there are areas of this process, steps in this process, that you are not clear about, then you should indicate that. And we should clarify the issue now rather than when you get to an exam. Are there any questions to begin with? If not, let's proceed to another example where t-testing is appropriate. Let's understand, first of all, as well, that there is a need, a primary need, to determine the critical value of the test statistic here, t. And that we need three pieces of information. We need to know whether the test is one or two-tailed. We need, secondly, to know the level of alpha. And third, we need to know the degrees of freedom. Let me read through an example. A researcher predicts that male members of an organization earn significantly more than female members. Let me ask you, just based upon that piece of information, what is the research hypothesis? What does the researcher predict will be the relationship between the average income of males and the average income of females? The prediction, would you agree, of the researcher is that X bar M, that is the average male salary, will exceed X bar F, that is the average female salary. So that the null hypothesis is that x bar m will be less than or equal to x bar f. Yes? Given this piece of information, that is, given the research hypothesis, should the test be one-tailed or two-tailed? The test should be one-tailed, because you're not being called upon to test simply for difference. Because of the nature of the research hypothesis, you do not have to test for the possibility that the average income of males will be less than the average income of females. You need to test only for positive difference in this instance, so that the appropriate test, is one-tailed. In order to test this hypothesis, the researcher measures the annual income of 32 selected members of the organization. 17 of the members are male. So if we go to the group of males, N1 equals 17. The mean income of these males is $29,324 a year. That is, X bar 1 equals 29,324. And the standard deviation of these scores is 1,743. That is, S1 equals 1,743. 15 members of the sample are female. That is, N2 equals 15. The average income of the 15, annual income of the 15 females is $28,191. And the standard deviation of those income scores is $3,325. Just as an aside, you understand that these standard deviation scores indicate that there's more variance in the female scores than in the male scores. Yeah? Let's set alpha equal to 0.05. Given sample size, how many degrees of freedom are there? The degrees of freedom are given by N1 minus 1 plus N2 minus 1, which in this case is 17 minus 1, which is 16, plus 15 minus 1, which is 14, so that there are 30 degrees of freedom. Would you agree? Given those pieces of information, what is the critical value of T? I've given you another table of T values. And let's just go through using this table of T values, because I think it's significantly more user-friendly. Down the extreme left-hand side, as is always the case, you have degrees of freedom. Across the top, you have level of significance for a one-tailed test, and then there are various levels of alpha going from 0.0005 to 0.10. You then have level of significance for a two-tailed test with a series of alpha values going from 0.001 to 0.20. Would you agree that we're conducting a one-tailed test here with alpha equal to 0.05, so that our interest is in the column of scores headed 6.314? Yes or no? Yes? There are 30 degrees of freedom. So we go down that column until we reach 30 degrees of freedom. Would you agree then that the critical t-score, t-value in this test is plus 1.697? You've now got one question right on the exam. Because on the exam, you will be asked to identify the critical value, the obtained value, and then evaluate the null hypothesis. So there will be sets of 3 questions. You've now got one question right. You're doing well. Everything is everything. Yes. Everything is not everything.
If it is a two-tailed test, then we divide alpha by 2 then?
What you would do with this table is you would simply go to level of significance for two-tailed tests. And if the alpha level for this test was 0.05, you would be interested in the column of figures headed 12.706. And with 30 degrees of freedom, the critical t-value would be plus 2.042. It would actually be plus and minus 2.042 if it were a two-tailed test. Are there any other questions? We need now then to determine or to compute the obtained or the observed value of the test statistic t. And we do that by invoking the only computational formula that we've encountered so far, and that is x bar 1 minus x bar 2 divided by the square root of s1 squared divided by n1 minus 1 plus s2 squared divided by n2 minus 1, which is 29,324 minus 28,191 divided by the square root of 1,743 squared divided by 16 plus 3,325 squared divided by 14. Yes? We're all going to plug and chug. We now take this time out for plugging and chugging. 1743 squared divided by 16 plus 3325 squared divided by 14 equals, should be something like 97,950, rather 979,565. And you want the square root of that, which should be something like 989.7. You now want to divide that into the difference between the means. The difference between the means is 1,133. What is your answer? Pardon? 4.34 we go for? No? The rest of you didn't do it. Nothing like dead air. What does anybody get here? Because I can tell you what I get.
After we get the square root of the 989, where do we go from there?
In terms of calculating this, what you have to do is divide the square root of that score into the difference between the two means. Now, you can do that in several ways. In terms of plugging and chugging, you can at that point take the square root of this score and write it down, and then you can subtract one mean, x bar 2, from x bar 1, and then you can divide by and then the score that you wrote down for the denominator. Alternatively, when you have computed the denominator, your calculator, because my calculator is 412 years old, your calculator should have a key on it that says 1 over x. If you hit this button, it will invert this denominator. And so rather than take the score out of the calculator, you can then multiply it by the difference between the two means. I've said previously that the plugging and chugging at some level is not important, and it's not. Preliminarily, it's not important. It's much more important that you understand the process. But plugging and chugging on the exam and doing it right is going to be important, because you either get the answer correct or you get it incorrect. So I'd like you to get some rehearsal at that by working your way through some of these examples as we go along. What answer, those of you who computed the obtained value of t, what answer did you get? And it doesn't matter. There's no embarrassment here if you got it wrong. I may well have got it wrong. Pardon? 1.12, 4.34, 1.14, 1.14. I got 1.14. It doesn't matter whether you're, at some level, it doesn't matter whether you're right or wrong. Yeah. It's important that you understand and ultimately memorize this formula. And it doesn't matter how you plug and chug your way through the formula. I don't care whether you're taking scores out of your calculator and writing them down, or whether you're proceeding some other way. This is not a course in how to best use your calculator. You progress through the plugging and chugging in the way that makes you feel most comfortable. The way in which you believe the probability is highest that you will come out with the correct answer. Let's assume that the correct answer in this case is plus 1.14. And I apologize for my writing, but it's a function of where they got the keys on this, because it's for right-handed people. I will say again with some animosity in my voice. Dell and the rest of these people ought to provide some sensitivity to left-handed people. If Michael Dell were left-handed, I suspect we would have a different computer. So, what do? We've gone through step 1, defining the critical value of t. We've gone through step 2, computing the obtained value of t. Now it's a matter of evaluating the null hypothesis. Would you conclude, A, that males earn significantly more than females, B, there is no significant difference between the annual income of males and females, Or would you conclude C, that females probably get a free ride in this organization anyway because they're not called upon to do anything that's at all cognitively substantive? I'm just joking for the females that now have there's a hit man, hit woman in here somewhere. We would conclude, first of all, that women are underpaid because they're obviously working substantially harder in this organization than males. The issue here is, would you reject the null hypothesis and conclude that males earn significantly more than females, or would you fail to reject the null hypothesis and conclude there is no significant difference between the annual incomes of males and females? All those who would reject the null hypothesis, just stick up your hand. All those that would fail to reject the null hypothesis. All those that are unsure. Okay. Let's go back to a sampling distribution of sample mean differences. A sampling distribution approaches normality even if the population is not distributed normally. Because we're talking about the sampling distribution of sample mean differences, the center of this distribution, mu, is equal to 0. That is where x bar 1 equals x bar 2. You understand, as you move away from the center of this distribution, either in a positive or a negative direction, the differences depart from 0. The differences between x bar 1 and x bar 2 depart from 0. Initially, they depart minimally from 0. But at the extremes, there is pronounced difference between x bar 1 and x bar 2. Either pronounced negative difference or pronounced positive difference. We could replace the word pronounced by significant difference. We drew a line in the sand. That is, we said at some point, up until some point, we're going to conclude that the difference between these two scores is not significant. Beyond that point, we're going to conclude that it is significant. And that point is the critical value of t. That is 1.697 standard deviations above the mean. In order for you and I to reject the null hypothesis and conclude significant difference, the obtained or observed value of t must be in this shaded region. If it is not in this shaded region, that is, if it's in this striped region, you and I, given the rules that we set up, would conclude that there is no significant difference between the annual income of males and the annual income of females in this organization. The obtained value of t was 1.14, somewhere in here. We agreed that we would reject the null hypothesis only if the obtained value was in this shaded region. Would you all agree then that given the rule that we set up, the decision-making rule that we established at the outset, we would fail to reject the null hypothesis? And when we fail to reject the null hypothesis, we would conclude that there is no significant difference between the annual income of males and females in this particular organization. Several of you said that you would reject the null hypothesis, and several more said that they were unsure how to make this decision. Would you still make the same decision if you were one of those who rejected the null hypothesis? And are you as unsure as you were before if you were one of those who said, I'm unsure what to do? We got another example of this to go through. I can make these up from now until Christmas. Wouldn't that be fun? We could play t-testing. That's what you do over the break. You meet up with your parents and you play a game of t-testing. I bet you do better than your parents in most instances. Not because you won't do it correct, but I'm assuming that in some instances your parents will be able to do this too. See, I'm figuring each of you will be able to do it. Okay, sports fans, we're on the road again. We're on the road again. I just can't wait to get on the road again. Passing my time singing Willie Nelson songs. Badly. A researcher predicts that married males watch significantly more television than unmarried males. We know this is true. Yeah. Married males, once they're married, man, we just sit down in front of that TV and suck it up. 24 hours a day. We'll watch nature shows. We'll watch sports events. We'll watch competitions between animals. 2 rabbits racing, 2 rabbits fighting, 3 rabbits fighting. That would be even better. We'll watch shows about people with a 165-pound tumor on their back. Yeah, wasn't that freaky? It's just freaky. It's just freaky. You see a woman who weighs 138 pounds, she's got toting around a 165-pound tumor on her back. It's not good. Things are not good. The good news is the tumor was removed and she lived a normal and happy life in Romania. She was not really Romanian. We just sent her to Romania afterwards to bring hope to the Romanian. No, she was Romanian. So, a researcher predicts, imaginatively, that married males watch significantly more television than unmarried males. Should the test be 1 or 2-tiled? If you didn't answer 1-tiled, first of all, you're incorrect, and secondly, it's getting to a point where you're in trouble. Had the researchers simply predicted that the amount of television watched by married and unmarried males differs, it would have been a 2-tiled test. Had the researcher predicted that unmarried males watch more TV than married males, the test would have been 1-tiled, because it predicts not simply difference, but difference in a particular direction. And so too does the researcher here, predicting that married males watch more TV than unmarried males. So that if group 1 is a group of married males and group 2 is a group of unmarried males, then the research hypothesis is that X bar 1 will be greater than X bar 2. You have simply the need to then to test for positive difference. That is, you need to test only one tail of this sampling distribution of sample mean differences, so that the test should be one-tailed. In order to test this hypothesis, the researcher measures the amount of television viewed by 122 randomly selected males. 62 are married. That is, N1 equals 62. And 60 are unmarried. N2 equals 60. When the researcher tests the hypothesis with alpha set to 0.05. We need to know three pieces of information to decide the critical value of T. We need to know whether the test is one or two-tailed. We need to know the level of alpha, and we need to know the number of degrees of freedom. How many degrees of freedom are there here? Would you all agree that the degrees of freedom here are 120? N1 minus 1 plus N2 minus 1, which is 61 plus 59, which is 120. We now use the T-table. The first thing we look for is level of significance for a two-tailed test with alpha a one-tailed test with alpha equal to 0.05. Would you agree that we are interested in the column of scores headed 6.314? With 120 degrees of freedom, would you agree that the critical value of T is plus 1.658? We need now to compute an obtained value of T. And to do that, we need to know X bar 1 and S1, and we need to know X bar 2 and S2. That is, the mean and standard deviation of the two sets of scores. Let's assume that the average amount of television viewing by the 62 married males is 4.21 hours per day, and that the standard deviation of those scores is 1.88. Let's imagine that the mean amount of television viewing by the 60 unmarried males is 2.26 hours a day, and that the standard deviation of those scores is 1.43. We then compute an obtained value of T by invoking the formula X bar 1, 4.21, minus X bar 2, 2.26, divided by the square root of S1 squared, which is 1.88 squared, divided by N1 minus 1, which is 61, plus S2 squared, which is 1.43 squared, divided by N2 minus 1, which is 59. Is anybody unclear on how we got to this point computationally? Then we enter into a moment's silence for the plugging and the chugging. This is going to drive subsequent students nuts, you know that? But they should be plugging and chugging along with us. So, sports fans, what do you have? What are you saying to me? Do I hear 1.6? Do I hear 2.0? Do I hear anybody say 2.6? 3.1? 3.8? 4.1? 5.2? 5.5? 5.9? 6.4? You go along with 6.4, 6.41, one of those two? I'd say 6.41. I'd say that the obtained value is 6.41. Actually, 6.408. 087. So, we have reached, as you would say in your culture, the point where the rubber hits the road. We have reached the bottom line. Something has hit the fan. We have reached the point of decision. Do you reject the null hypothesis, or do you fail to reject the null hypothesis? Oh, it's like a choir. It's like a choir singing in harmony. We reject the null hypothesis. We're going to take it out and kill it. You reject the null hypothesis. Because the obtained value of t is in, if you go back to the graphic representation of this, of the sampling distribution of sample means, any obtained value of t in excess of 1.658 was going to be reason for us to reject the null hypothesis. We have an observed value of plus 6.41. We therefore reject the null hypothesis. We conclude that in fact married males watch significantly more television than unmarried males. Are there any questions initially about going from statements of we reject the null hypothesis to the statement that casts that in terms of the issue? That is, when you reject the null hypothesis in this instance, what you conclude is that married males watch significantly more television than unmarried males. Are there any questions at all? Yes. Would you like to press and?
Since we have a more detailed table of T, we don't have to divide alpha by 2 anymore, even if it's a 2-cell test. Or
The T table that I distributed, I think, is significantly more user-friendly because it distinguishes between 1- and 2-tailed tests. So that if you are conducting a 1-tailed test, you simply locate the appropriate alpha value under level of significance for a one-tailed test. So if alpha is 0.05, it's a one-tailed test. You're interested in the column of scores headed 6.314. You don't have to divide anything by 2. If you are conducting a two-tailed test and alpha is 0.05, you're interested in the column of scores headed 12.706. To allay another potential concern, this t-table, like any t-table in any text, is limited. It contains no degrees of freedom, for example, between 30 and 40. It contains no degrees of freedom between 40 and 60 or 60 and 120, and it contains no degrees of freedom in excess of 120. And one question that may lead to is what happens on an exam if we've got 64 degrees of freedom? If you compute my answer, if you compute the degrees of freedom and you've got 64, you're wrong. Or I have made a mistake in typing up the exam. On the exam, the degrees of freedom that you need will be one of the values on here. Okay. Yes.
How would we evaluate the null hypothesis on a two-tailed?
On a two-tailed test? Suppose in this instance, the researcher had predicted simply that married and unmarried males watch different amounts of TV. That test would have been two-tailed. Would you agree? That is, we would now be dealing with a two-tailed test rather than a one-tailed test. But nothing else would change. That is, we could retain alpha at 0.05 and the degrees of freedom would still be 120. But what would change would be the critical value of t. And the critical value, to determine the critical value of t, we would go to the t-table that I distributed, level of significance for a two-tailed test with alpha equal to 0.05. You're interested in the column of scores headed 12.706. Because you have 120 degrees of freedom, the critical t value, would you agree, is plus and minus 1.98. Yes? The decision rule that you've set up now, if we go back to the sampling distribution of sample mean differences, because you're testing for both positive and negative difference, you have to test both tails, that is, two tails of the distribution. You need to define, operationalize, what constitutes alpha equal to 0.05 in a two-tailed test. And we've done that. We have to go out 1.98 standard deviations in each direction so that we isolate 0.025 of all of the scores at this end of the sampling distribution and 0.025 of all the scores at the positive end of the distribution, so that the overall alpha is 0.025 plus 0.025, which is 0.05, which is what we said here. Yeah? So minus 1.98 plus 1.98. This means that we will now reject the null hypothesis if, on the one hand, the obtained value of t is less than 1.98, that is, it's in this shaded region at the negative end of the distribution, or if the obtained t-value is greater than plus 1.98. That is, it's in this shaded region at the positive end of the distribution. Would you agree that changing the test from 1 to 2 tiled doesn't affect the obtained value of t? We have an obtained value of t of 6.41, which is that is a score that's a difference score that is 6.41 standard deviations above the mean. Would you all agree that we would continue to reject the null hypothesis? And we would conclude in this instance that there was a significant difference, because that's what we were testing for, difference, not more than, not less than. We would conclude that there was a statistically significant difference between the average amount of television viewed by married and unmarried males. That there is a difference.
What was that hypothesis for the two-tailed again?
The research hypothesis for a two-tailed test would be that X bar 1 differs from X bar 2. No, there's always the notion of differs significantly. This is the critical issue in determining 1 or 2 tiled. If the research hypothesis is simply one of difference, then you have to test for both negative difference and you have to test for positive difference. That is, you have to test both tiles of the distribution so that the appropriate test is 2 tiled. If, however, the researcher predicts only negative difference, then the appropriate test is 1 tiled, because the only burden on the researcher is to test for negative difference. If the researcher predicts positive difference and only positive difference, then the appropriate test is 1 tiled, because all the researcher has to do is test for positive difference. That is, test 1 tile of the sampling distribution of sample mean differences. Your question is, so the question is who watches more?
Yeah.
If the test is 2 tiled, no. The question is not who watches more. The question is either, is there a significant difference between the amount of TV watched by the 2 groups, or do the unmarried males watch significantly more TV than the married males? The unmarried males, or it's do the married males watch significantly less TV than the unmarried males? You've got 3 options for a research hypothesis. Option 1 is X bar 1 differs from X bar 2. Do married and unmarried males watch significantly different amounts of television? 2 tiled. X bar 1 is greater than X bar 2. Married males watch significantly more TV than unmarried males. 1 tiled. Option 3, X bar 1 is significantly less than X bar 2. That is, married males watch significantly less TV. Married males watch significantly less TV than unmarried males. 1 tiled test. Because in this instance, in the first instance, you have to test for positive and negative difference. In the second instance, you have to test only for positive difference. And in the third instance, you have to test only for negative difference. So the determination of whether the test should be 1 or 2 tiled is in the research hypothesis, what the researcher predicts. Are there any other questions? look over your notes. We will go through one more example of t-tests on when we next meet. Well, when we next meet, and we will also go through scenarios, general scenarios, so that, hang on a second, I know this is leave-taking behavior. I study interpersonal communication, I know this stuff. We will also go through a number of scenarios so that you can get used to determining whether you need to perform a z-test or a t-test. And then we will move into analysis of variance. Analysis of variance is a data analytic technique used when you're dealing with more than two groups. And you should read ahead, because this becomes, obviously, the more balls you have in the air, the more complicated this becomes. However, you're always going through the same process, and ultimately you're asking the question, does this group differ from this group? Read through the chapter that deals with analysis of variance, or the pages that I pointed to in the text, and don't stop. If you become totally confused, read on. Yeah. Get to the end of the chapter, go and pour yourself a glass of tequila, drink the tequila, and then go back to the beginning of the chapter again. It will appear so much easier. I will see you next time.